Introduction. Today I'll teach you the topic Structure of Atom. Atoms are the fundamental units of matter. Everything around us is made up of atoms. A typical atom consists of a nucleus of protons and neutrons with electrons orbiting this nucleus. Sir, I have a question. All objects around us are made up of different materials. So how it is possible that atoms are fundamental unit of matter? Good question, Rakesh. As you know that all objects are made up of different material like plastic, rubber, iron, etc. They have different arrangement and types of molecules. And molecule is a group of two or more atoms. So the fundamental unit is atom. So students, let us discuss more about the atoms. Objectives. At the end of this lesson, you'll be able to know Thomson's model of atom, describe alpha particle scattering experiment, understand alpha particle scattering experiment, describe Rutherford's model of atom, define electron's orbit, analyze atomic spectra, describe Bohr's model of the hydrogen atom, know about energy levels of hydrogen atom, analyze line spectra of hydrogen atom, know about de Broglie's explanation of Bohr's second postulate. Thomson's model of atom. In 1898, J.J. Thomson suggested a model of atom, sometimes called plum pudding model. He supposed the atom to be full of some positive fluid, like a pudding, in which electrons were embedded like plumes in that pudding. The radius of the spherical model was about 10 raised to the power minus 8 centimeter. The total positive charge in the positive fluid was evenly and symmetrically balanced by the negative charges of the electrons. But this model was discarded because it failed to satisfy the result of the experiments performed by Rutherford. Alpha particle scattering experiment. Rutherford's experiments consisted in projecting alpha particles into thin foils of metal and by observing the trajectories in which the projected particles were deflected. Experimental setup. The alpha particles emitted from a radioactive source were collimated by the lead bricks into a narrow beam. The beam was then projected into a thin metal foil of thickness 2.1 into 10 raised to the power minus 7 meter. The scattered alpha particles on striking a rotable zinc sulfide screen produced scintillations which could be viewed through a microscope. Observations. Most of the alpha particles passed straight through the metal foil as if it were empty space. Only about 0.14% of the incident particles scattered by more than 1 degree. A small fractions were scattered through large angles greater than 90 degree, with some of these getting scattered by angles of nearly 180 degree. Rutherford developed a theory assuming that the alpha particle and the nucleus are point masses and charges. Only an electrostatic repulsive force acts between the alpha particle and the nucleus. The nucleus is so massive compared with alpha particle that it does not move during the interaction. Alpha particle trajectory. Since the electrostatic force varies with 1 upon r square, the alpha particle's trajectory is hyperbola, where r is the instantaneous separation between alpha particle and nucleus. The perpendicular distance between the nucleus and the initial line of motion of an alpha particle is called the impact parameter. Rutherford calculated the number n theta of alpha particles per unit area that reach the screen at a scattering angle of theta and found that n theta is inversely proportional to sin theta upon 2 raised to the power 4. The distance of closest approach between the particle and the nucleus suggested the size of the nucleus to be about 10 raised to the power minus 14 meter to 10 raised to the power minus 15 meter. Any electrons belonging to the atom were assumed to be in the relatively charged volume outside the nucleus. With the atom being largely empty space, most alpha particles thus passed through the thin foil undeflected. Rutherford's model of atom. The Rutherford scattering experiment led to the nuclear atom model, the main features of which are: an atom consists of a positively charged and massive core called the nucleus. The nucleus occupies a very small space as compared with the size of the atom. The nucleus is surrounded by an adequate number of electrons so that the atom is electrically neutral. To keep the electrons in place against the electric force attracting them to the nucleus, they revolve around the nucleus in orbits. Electrons orbit. The Rutherford nuclear model of the atom pictures the atom as an electrically neutral sphere consisting of a very small, massive, and positively charged nucleus at the center, surrounded by the revolving electrons in their respective dynamically stable orbits. The electrostatic force of attraction between the revolving electrons and the nucleus provides the requisite centripetal force to keep them in their orbits. Fe is equal to Fc. Putting their respective values, we get mv square by r is equal to 1 upon 4 pi epsilon naught E square upon R square. We can also write this equation as R equals E square upon 4 pi epsilon naught mv square. The kinetic energy and electrostatic potential energy of the electron in hydrogen atom are given by K equals 1 upon 2 mv square, which equals E square upon 8 pi epsilon naught R, and U is equal to minus E square upon 4 pi epsilon naught R. Thus, the total energy of the electron in a hydrogen atom is given by E as K plus U, which is equal to minus E square upon 8 pi epsilon naught R. The total energy of the electron is negative. It means that the electron is bound to the nucleus. Atomic spectra. An evacuated glass tube filled with a glass such as hydrogen can be made to emit electromagnetic radiation by applying a sufficiently large potential difference between two electrodes located within the tube. If the emitted lines are analyzed, a series of discrete lines are observed, each line corresponding to a specific wavelength. Such a series of bright lines on a dark background is called an emission line spectrum. When white light passes through a gas, the transmitted light consists of some dark lines. These dark lines are called the absorption line spectrum of the material of the gas. The group of lines in the visible region is known as the Balmer Series. These lines can be described by equation 1 upon lambda equals R 1 upon 2 square minus 1 upon n square. Here value of n may be 3, 4, 5 and so on, where R is Rydberg constant having value 1.0973732 into 10 raised to the power 7 per meter. The other series of lines exist outside the visible region are Lyman series, which is given by 1 upon lambda equals R 1 upon 1 square minus 1 upon n square. Here value of n may be 2, 3, 4, 5 and so on. Bastian series, which is given by 1 upon lambda equals R 1 upon 3 square minus 1 upon n square. Here value of n may be 4, 5, 6, 7 and so on. Bracket series, which is given by 1 upon lambda equals R 1 upon 4 square minus 1 upon n square. Here value of n may be 5, 6, 7, 8 and so on. Pfund series, which is given by 1 upon lambda equals R 1 upon 5 square minus 1 upon n square. Here value of n may be 6, 7, 8, 9 and so on. Bohr model of the hydrogen atom. The basic postulates of the Bohr model of the atom are: the electron moves about the nucleus under the influence of the Coulomb force in special circular orbits called the stationary orbits. In these orbits, electron does not radiate electromagnetic waves, hence the atom is stable. The stationary orbits are those for which the angular momentum L of the electron is an integral multiple of h upon 2 pi. L equals nh upon 2 pi, where n is known as quantum number of the orbit and h is Planck's constant. If the electron makes a transition from one stationary orbit to another stationary orbit, it emits a photon of frequency nu, given by EI minus EF upon h. Radii of the Bohr orbits of hydrogen atom. We know that for hydrogen atom, radius of circular orbit is given by E square upon 4 pi epsilon naught mv square. We have to find the radius of nth orbit that satisfy the Bohr quantization condition on angular momentum. Ln is equal to product of m, Vn and Rn, which equals to nh upon 2 pi, where n is equal to 1, 2, 3 and so on. And Vn is the speed of the electron in nth orbit. This equation can be written as Vn equals nh upon 2 pi mRn. On comparing the above two equations, we get the expression of velocity and radius of nth orbit. Vn equals 1 upon n multiplied by E square upon 2 epsilon naught h, and Rn equals to n square multiplied by h square epsilon naught upon pi m E square, which equals n square A naught, where A naught is equal to 0.529 angstrom. Energy levels for hydrogen atom. We know that the total energy of hydrogen atom is the sum of the kinetic energy of the electron and its potential energy in the Coulomb field of the nucleus. En equals minus E square upon 8 pi epsilon naught Rn. This equation can also be written as En equals minus me raised to the power 4 divided by 8 epsilon naught square n square h square, where E naught is equal to me raised to the power 4 divided by 8 epsilon naught square h square. En equals 2.2 into 10 raised to the power minus 18 joule, which is equal to 13.6 electrovolt. The above equation can also be written as En equals minus 13.6 upon n square electrovolt. The energies specified by these equations are called the energy levels of the hydrogen atom. These levels are negative, signifying that hydrogen atom is a bound system. The lowest stationary energy state, called the ground state, corresponds to n as 1 and has an energy E1 equals minus 13.6 electrovolt. The next state, called the first excited state, corresponds to n as 2 and has an energy E2 equals minus 3.4 electrovolt and so on. As the quantum number increases, the corresponding energy approaches closer to zero. The minimum energy required to free the electron from the ground state of an atom is called the ionization energy of the atom. Thus, the ionization energy for hydrogen atom is 13.6 electrovolt. Example. Let's take an example of Bohr's model of the hydrogen atom. Let's see the solution. Find the ratio of minimum to maximum wavelength of radiation emitted by electron in ground state of Bohr's hydrogen atom. Energy of radiation corresponding to transition between two energy levels N1 and N2 is given by 13.6 multiplied by 1 upon N1 square minus 1 upon N2 square electrovolt. E is minimum when N1 is equal to 1 and N2 is equal to 2. E minimum is equal to 13.6 into 3 upon 4 electrovolt. E is maximum when N1 is equal to 1 and N2 is infinity. E maximum is equal to 13.6 electrovolt. Now taking ratio of E minimum and E maximum, we get E minimum upon E maximum as 3 upon 4, or lemma minimum, lemma max equals 3 upon 4. Hence, the ratio of minimum to maximum wavelength of radiation emitted by electron in ground state of Bohr's hydrogen atom is 3:4. The line spectra of hydrogen atom. In an assembly of atoms, an ordinary temperature, most of the atoms lie in the ground state. If white light is passed through such an assembly of hydrogen atoms, the transmitted light will not have radiations of various wavelengths. It is the absorption spectrum of hydrogen corresponding to Balmer series. An absorption spectrum is obtained when electron from lower energy state goes to higher energy state after absorbing energy from radiation. the frequency of absorbed radiation is given by h nu HL equals E high minus E low. At room temperature, there are very few electrons in higher energy states, n as 2 and 3. The number of electrons in various energy states is determined by the temperature. At higher temperature, hydrogen have sufficient number of electrons in state n as 2. The wavelength of absorption lines will be same as that of emission lines. This relation is used to calculate the frequency of absorbed light as that of emitted light. E2 minus E1 equals h nu 12, which is equal to hc upon lemma 12. de Broglie's explanation of Bohr's second postulate of quantization. De Broglie explained the quantization condition on angular momentum of an orbiting electron. According to de Broglie, when an electron is in a stationary orbit of an atom, it is in a kind of resonance. The resonance condition on the wavelength of the electron requires that a standing wave is maintained over the circumference of its orbit. Hence, the circumference of the electron's orbit contains an integral number of its de Broglie wavelengths. 2 pi r equals n lemma, where n is equal to 1, 2, 3, and so on. For an electron of mass m and speed v, the de Broglie wavelength is given by h upon mv. This may be written as mvr equals nh upon 2 pi. This is the Bohr's angular momentum quantization condition. Did you know? The number of atoms in the universe is about 10 followed by 80 zeros. Under certain conditions, atoms can be split into over 200 kinds of short-lived subatomic particles. The particles of the nucleus are made from various even tinier particles called quarks. In the 1890s, scientists thought that atoms were solid like billiard balls and completely unbreakable. Electrons are 1,836 times as small as protons, so they weigh almost nothing. Summary. Let us summarize what we have learned. The distance of closest approach between the particle and the nucleus suggested the size of the nucleus to be about 10 raised to the power minus 14 meter to 10 raised to the power minus 15 meter. An atom consists of a positively charged and massive core called the nucleus. The nucleus occupies a very small space as compared with the size of the atom. The nucleus is surrounded by an adequate number of electrons so that the atom is electrically neutral. The electrostatic force of attraction between the revolving electrons and the nucleus provides the requisite centripetal force to keep them in their orbits. When white light passes through a gas, the transmitted light consists of some dark lines, called the absorption line spectrum of the material of the gas. The electron moves about the nucleus under the influence of the Coulomb force in special circular orbits called the stationary orbits. The minimum energy required to free the electron from the ground state of an atom is called the ionization energy of the atom. An absorption spectrum is obtained when electron from lower energy state goes to higher energy state after absorbing energy from radiation.